We know already that if I were to throw a brick at you, it would cause pain, it would hurt, because it has kinetic energy, right? Energy due to its motion. But what if I took that same brick and I held it high over your head? Does it have energy now? Can it cause pain? The answer is yes, and today we're going to explain why. But before we do, the first person to email me and tell me the color of my tie will get a 100 on the assignment of their choice from the energy unit. First, we'll classify all forces as being either conservative or non-conservative. A conservative force will transform energy within a system, while non-conservative forces will transfer energy into or out of the system. This distinction is important because when work is done against conservative forces, it's stored as potential energy. We can think of it as having the potential to cause pain. Potential energy is due to an object's position in or the configuration of a system. And for our purposes, our systems will generally consist of the object, the earth, and a spring or a spring-like material. We're going to focus on two types of potential energy. First is when work is done against gravity. So say we have a box that we're holding here above the earth. First, we're going to define our system. Our system consists of the object, the box, and the earth. We know that gravity is going to always act down. So if I lift the box against gravity, there's going to be a change in its energy. That work I do lifting the box against the conservative force of gravity is stored as potential energy. And that energy equals the work done against gravity. So that potential energy equals the force, or the weight of the object, times the height it was lifted. Next, we'll talk about when work is done against an elastic force. Here we have a box or a block that's attached to a spring on some frictionless surface. So our system will consist of the object and the spring. If I push the box to the left and compress the spring, work is done against an elastic force. The work done against this elastic force is stored as potential energy, and the amount of potential energy is going to equal 1/2 the K, which is a spring constant, multiplied by how far it was stretched or compressed, that quantity squared. Both these systems have the potential to cause pain, but unless something changes, they won't. So only changes in potential energy are going to be significant. So what happens when the system is allowed to change? When work is done by a conservative force, there'll be a decrease in the potential energy. So when we did work against gravity, that work was stored as potential energy. Now if we allow gravity to do work and let the box fall, that potential energy will decrease as a result. An important thing to remember is that an object by itself cannot have potential energy. The system must include the earth, the spring, or both, right? Because without the earth, there's no gravitational force. So if there's no gravitational force, you can't do work against the gravitational force for it to be stored as potential energy. Same thing with the spring. Without the spring, there's no elastic force. So I can't do work against a non-existent elastic force, so that work can't be stored as potential energy. Kinetic and potential energies combine to form what we call mechanical energy because they relate to the motion of an object. Let's take a look at two questions related to potential energy. First, rank in order from largest to smallest the gravitational potential energies of the identical balls 1 through 4. So the balls are the same, the only difference is going to be their heights. So the gravitational potential energy would equal the weight of each ball times its height. And since the balls are identical, they all have the same weight. So the only thing that's going to matter is their height. And we can see that 3 is the highest, 2 and 4 have the same height, so they're going to equal each other. and then all three of them are greater than 1. Their speeds there don't matter, only how high they are above the ground. When a spring is stretched by 5 centimeters, its elastic potential energy is 1 joule. What will its elastic potential energy be if it's compressed by 10 centimeters? So it was stretched 5 and it was compressed 10. So kinetic energy, or elastic potential energy rather, is 1/2 kx squared. So our spring constant will always be positive, and our x, because we're squaring it, will always be positive. So as a result, we can't have negative elastic potential energy. All right, the direction doesn't matter, whether it's stretched or compressed, because again, we're squaring that x. So even if we stretch at 5, compress at 10, we don't care if it's stretched or compressed. We're about the 5 centimeters and the 10 centimeters. So 10 centimeters is twice the size of 5, but because that x is squared, 2 squared is 4, it would result in 4 times the elastic potential energy.